Hello and welcome to listening to the radio.
Isn't it incredible? You think about a radio signal, just this tiny bit of energy, and somehow it travels clear across continents. It really feels like it's bouncing off thin air.
It does seem almost magical, doesn't it?
Yeah. So today on the deep dive, we're going to unpack that magic. We're talking about the propagation of shortwave radio waves.
Exactly. We'll be looking at the HF range, that's 3 to 30 megahertz. Our sources really get into the science behind how these signals go so far. It's all about Earth's atmosphere and, crucially, what the sun is doing.
Right. So the mission here isn't just to say, wow, shortwave signals travel far. We want to dig into the why and the how. What are the key things making these long-distance radio chats possible?
Okay, so let's start with the basics, the atmosphere itself.
Our planet's air blanket.
Precisely. Think of it as this incredibly thin layer of gas wrapped around Earth. It goes up about 600 kilometers, maybe a bit more.
Which sounds like a lot, but when you compare it to the Earth's diameter,
Yeah.
what is it, nearly 13,000 kilometers?
Exactly, around 12,742 kilometers. So that image you always see from space, that thin blue line, it really drives home how relatively thin the atmosphere is.
It really does. And it's mostly nitrogen and oxygen, right?
Yep, about 78% nitrogen, 21% oxygen, and then just 1% of, other bits and pieces.
But it's not just one uniform soup all the way up, is it? There are layers.
That's right, several layers. But for shortwave radio, the real star of the show is the ionosphere.
The ionosphere, okay. Where is that located?
It starts around 80 kilometers up and extends out to maybe 600 kilometers or so. And like the name suggests, it's full of ions, electrically charged particles.
Okay, so ions. What makes this ionosphere layer so special for radio waves traveling thousands of miles?
Well, its big trick is that it can reflect radio waves, or maybe refract is a better word, bend them back towards Earth.
Okay, reflect or refract them. How does it do that?
It's down to free electrons. The ionosphere has a lot of them floating around. Think of them like tiny little mirrors scattered through that region of the atmosphere.
Free electrons acting like mirrors, where do they come from?
They get knocked loose from atoms and molecules by the sun's energy. It's a process called ionization.
Ah, ionization.
Yeah. The upper atmosphere gets hit by really intense solar radiation, powerful stuff like X-rays, gamma rays, and ultraviolet light. This energy is strong enough to strip electrons away from the gas atoms up there, like oxygen and nitrogen, and even traces of things like sodium.
And when an atom loses an electron...
It becomes an ion, yeah. An ion is just an atom or molecule with a net electrical charge because it's lost or gained an electron.
It's amazing that this layer, the ionosphere, making up less than 1% of the whole atmosphere, is so absolutely vital for this kind of communication.
It really is.
Yeah.
And here's a slightly confusing bit. While we call it the ionosphere because of those ions, it's actually the free electrons that get knocked loose that do most of the heavy lifting when it comes to affecting radio waves.
So the electrons are the key players for radio propagation.
Primarily, yes. And this ionization process, it mainly happens on the side of the Earth that's facing the sun. Makes sense, right? That's where the solar radiation is hitting directly.
Right, you need that intense energy.
Especially the shorter wavelengths, like extreme UV and X-rays. They pack the punch needed to create enough free electrons.
So daytime is prime time for ionization.
Generally speaking, yes. The number of free electrons starts picking up around 30 kilometers altitude. But you don't really get enough density to significantly bend those HF radio waves until you're above about 60 kilometers.
Okay. And scientists divide this ionosphere up, don't they, into different layers?
They do, historically. It helps explain things.
Yeah.
You'll hear about the D, E, and F layers. Our sources have diagrams showing them at different altitudes.
D being the lowest, then E, then F up higher.
Exactly. Think of it like zones where the electron concentration peaks. It's not like sharp boundaries, more like regions. There's mention of a C layer, too, but it's too weakly ionized to matter much for radio.
So D, E, and F are the main ones we care about.
Pretty much. And it's worth noting, the sun isn't the only thing causing ionization, though it's the biggest factor by far.
Oh, what else?
Well, up near the poles, you have auroras, those beautiful lights. They're caused by charged particles from space, guided by Earth's magnetic field, crashing into the atmosphere and causing ionization.
Right, the northern and southern lights.
And near the equator, there's something called the equatorial anomaly. Basically, peaks of ionization caused by complex interactions between the Earth's magnetic field and atmospheric winds.
Wow, okay. It's definitely not simple. Now, figuring all this out must have taken some time, right? This understanding didn't just pop up overnight.
Not at all. It was a slow burn, piece by piece. Our sources trace it back quite a way. Even in 1839, Carl Friedrich Gauss was speculating about electrical currents high up causing daily magnetic field changes. He suspected ionized regions existed.
Way back then, before radio was even a thing, really.
Right. And then in 1878, Balfour Stewart proposed a conductive layer to explain those magnetic variations. Early hints.
But things must have really kicked off with Marconi.
Definitely. His famous transatlantic transmission in 1901, that was a puzzle. How did the signal get around the curve of the Earth? It was only 300 kilohertz, quite a low frequency.
Yeah, radio waves travel in straight lines, don't they? So something must have bounced it.
Exactly. And in 1902, Kennelly in the U.S. and Heaviside in the U.K. independently came up with the idea there must be an ionized reflective layer high up.
The Kennelly Heaviside layer, as it became known.
That's the one. Then things moved forward. Around 1910, Austin came up with formulas for long-wave signals and even thought 1.5 millihertz was maybe the upper limit for long distance.
Huh. He was way off there.
He was, but it was based on what they knew. In 1912, Eccles suggested solar radiation was what maintained this layer. The sun's role was becoming clearer.
Connecting the sun to the radio signals.
Then, between 1920 and 24 came the big surprise. Radio amateurs and experimenters discovered that shortwave frequencies above 1.5 millihertz all the way up to 30 millihertz actually worked really well for long distance.
That must have flipped things on their head.
It really did. Larmor developed the theory in 1924, explaining how free electrons could refract these higher frequencies. Then came the proof.
Experimental proof.
Yes. In 1925, Appleton and Barnett actually measured the height of the layer by comparing radio signals. Real, concrete evidence.
That's huge, actually measuring it.
And then Bright and Tuve, in 1926, used pulses like radar, really to measure the height in critical frequencies. That was the first ionoson, basically the first tool to actively probe the ionosphere.
So the tool started developing, too.
Absolutely. Chapman's theory of layer formation by UV came in 1931, and Appleton refined the math in 32, including absorption and magnetic field effects. So by the early 30s, the basic picture was largely in place.
What a fascinating journey of discovery. Okay, so we have the ionosphere, created by the sun, acting as our radio mirror. Now let's talk about how changes in the sun affect this mirror.
Right. This is where we get into space weather. If you ever looked at amateur radio websites, you've probably seen those propagation banners or dashboards.
Yeah, with all the numbers and charts, SFI, K-index.
Exactly. A lot of those were developed by Paul Herman and Zero and BH. They give us a snapshot of what the sun's up to. And the sun is, well, it's busy. It's constantly sending out electromagnetic radiation, the ionizing stuff, but also radio noise plus streams of particles.
Solar wind, right, and those big eruptions.
Yep, the solar wind full of protons and electrons, and sometimes huge blasts called coronal mass ejections, CMEs. All this solar output affects the ionosphere.
Okay, let's break down some of those key numbers on the banners. What's the solar flux index, SFI?
SFI measures the sun's radio noise output at a specific frequency, 2800 megahertz or 10.7 centimeter wavelength. It ranges roughly from 60 up to 300 or so.
And what does it tell us about propagation?
Generally, higher SFI is better, especially for the higher HF bands. Think 20 meters up to 10 meters. An SFI above 100 is usually seen as favorable. Now, that 2800 megahertz signal itself isn't ionizing our atmosphere,
Okay.
but it's a really good proxy. It correlates well with the sun's output of the extreme ultraviolet, UV, and X-rays that do cause the ionization. So high SFI suggests high ionizing radiation.
Got it. So it's an indicator. What about sunspots, the sunspot number, SN?
Sunspots are areas of intense magnetic activity on the sun. The sunspot number isn't just a count. It considers the number of spots, groups, and their size. It ranges from 0 up to maybe 250 or more at solar maximum.
And more sunspots means?
More sunspots generally means more UV and X-ray radiation. This boosts ionization in all the key layers, D, E, and F. That usually raises the maximum usable frequency, MUF, and generally improves HF conditions overall.
So high SFI, high sunspot number, generally good news for shortwave listeners and hams. What about X-ray intensity, RXY?
This measures the intensity of X-rays hitting Earth. They're class B, C, M, and X, with each class being 10 times stronger than the last. B and C flares are usually minor.
But M and X?
M and especially X-class flares can be trouble, particularly during the day. They dramatically increase ionization way down in the D layer.
And the D layer absorbs radio waves, right? Especially lower frequencies.
Exactly. Normally, the D layer absorbs the lower bands, like 160 and 80 meters during the day. But a strong flare can make it absorb much higher frequencies too, sometimes causing a complete radio blackout on the sunlit side of the Earth for minutes or even hours. It really hits the lower bands hard.
Yikes. So a big X-ray spike is bad news for daytime HF. What's the 304A number?
That refers to radiation at 304 angstroms, which is in the extreme ultraviolet range. This specific wavelength is actually responsible for about half the ionization of the F layer, the really important one for long-distance stuff.
Ah, so it directly relates to the key layer.
It does. It tends to track with the SFI, so higher values usually mean better F layer conditions.
Okay, now things get a bit more complex. Interplanetary magnetic field, BIRS.
Right, the BIRS component. This tells us about the magnetic field carried by the solar wind, specifically its north-south orientation relative to Earth's own magnetic field.
And why does that matter?
If the BIRS is negative pointing south, opposite to Earth's northward field, it's like opening a door. It allows more energy and particles from the solar wind to get into our magnetosphere.
Which can cause problems.
Yes, it can lead to geomagnetic disturbances and storms, which often disrupt the ionosphere, particularly the F layer, making HF propagation unstable or poor. A strong negative BIRS is often a warning sign.
Okay, so negative B's potential trouble. What about solar wind speed, SW?
That's just how fast the solar wind particles are flowing past Earth. Normal is maybe around 350–400 kilometers per second.
And if it gets faster?
If it jumps up significantly, say above 500 kilometers, maybe from a CME or a coronal hole, that fast wind puts pressure on the magnetosphere. This can compress and disturb the ionosphere, often leading to degraded HF conditions.
So too fast isn't good either. What about proton flux, a PF, and electron flux, EPF?
These measure the density of high-energy protons and electrons arriving, particularly near Earth. High levels, especially protons, can cause increased ionization over the polar regions.
Which affects signals going over the poles.
Exactly. It can lead to polar cap absorption events, basically blacking out HF signals on polar paths. High electron flux is more linked to auroral activity.
And the signal noise level, is that just static?
It's related to the background noise generated by the solar wind interacting with our magnetic field. Higher solar activity can raise the noise floor, making weak signals harder to hear.
Then we have CMEs, coronal mass ejections. Those sound dramatic.
They are huge clouds of plasma and magnetic fields blown off the sun. If one hits Earth, usually a day or two after leaving the sun, it can trigger major geomagnetic storms.
And the banners often predict their arrival and strength.
Yes, often with a green, yellow, red warning for minor, moderate, or severe impact. Severe CMEs cause the biggest disruptions to radio, power grids, satellites, the works.
Which leads us to the K&A indices. These seem like the bottom line for geomagnetic activity.
They really are key indicators. The K index measures magnetic field disturbance over a 3-hour period on a scale of 0 to 9. Higher numbers mean more disturbance. K values of 4 or more usually indicate storm conditions.
And the A index.
The A index is a daily average based on the K indices from the previous 24 hours. It gives a broader picture of the geomagnetic climate. Lower A and K are generally much better for stable HF propagation.
Is there a sweet spot?
Well, very low A indices, like 1 to 6, often favor the higher bands, 10 through 20 meters. Slightly higher A, maybe 7 to 9, can sometimes correlate with better conditions on the lower bands, 30 through 160 meters, especially at night. But generally, low is good. High means the F layer is likely choppy and unreliable.
And this relates to the aurora reading, too.
Yes, the AUR value estimates the energy hitting the poles. Higher values mean more intense auroras, expanding further from the poles. The latitude value indicates how far south, or north in the southern hemisphere, the aurora might be visible.
Auroras are beautiful, but bad for polar HF paths.
Often, yes. While they can cause some unusual VHF propagation, they tend to absorb or scatter HS signals passing through those regions.
Okay, MUFBDR, maximum usable frequency from Boulder.
Exactly. It's an estimate based on measurements usually taken in Boulder, Colorado, of the highest frequency likely to work via the ionosphere at that specific time. Gives you a real-time idea of how high in frequency you can expect signals to propagate.
And EME degrees. Earth. Moon Earth. That sounds very specific.
It is. It's for people who bounce signals off the moon. The EME degradation value indicates how much extra signal loss is expected on that path due to ionospheric conditions. Higher numbers mean tougher conditions for moon downs.
Wow. Finally, the overall geomagnetic field state.
That's just a summary, usually based on the K index telling you if the field is quiet, unsettled, or at various storm levels. Major storm levels usually mean widespread HF problems and potentially visible auroras at lower latitudes.
So putting it all together, for generally good conditions, we want high SFI and sunspot numbers, but low K&A indices. A sort of active sun, but a calm Earth magnetic field response.
That's a pretty good simplification, yes. But remember, it's not just the sun's current stats. Time of day is huge.
Right, day versus night.
Seas makes a difference too. Your location on Earth matters. And the big one is the 11-year solar cycle, where we are in that overall pattern of high and low activity dramatically changes things, especially on the higher bands.
And different bands behave differently too, don't they?
Absolutely. The lower bands, 160, 80, maybe 40 meters, they're often best at night because the D-layer absorption disappears after sunset.
Makes sense.
The higher bands, 20, 17, 15, 12, 10 meters, they usually need strong daytime ionization in the F layer, so they work best during the day,
Right.
especially when solar activity is high.
But sometimes storms can cause weird openings.
Or they can. Sometimes a big solar event can temporarily supercharge the ionosphere and create unexpected propagation on bands that are normally quiet. It's always dynamic.
Okay, that's a great look at the solar side. Our other source dives into the specific bands themselves, right? Gives a feel for each one.
Yes, it provides a kind of personality profile for each amateur band within that HF range. It talks about the general split: high bands, 14 megahertz and up, mostly daytime; low bands, below 14 megahertz, mostly nighttime. 14 megahertz or 20 meters is often seen as the bridge.
And it mentions the gray line.
That terminator, the line between night and day moving across the Earth. Because the D-layer is weak or absent along that line, you can sometimes get enhanced propagation for short periods between places that are both near sunrise or sunset.
Cool effect. Okay, let's quickly run through the bands, starting low, 160 meters.
Top band, primarily a night band. That D-layer kills it during the day. At night, you can work regionally, nationally, sometimes even other continents via the F layer. Can be very noisy, though, lots of static, especially in summer.
80 meters.
Similar story, mostly a night band. F layer propagation after dark. Daytime absorption is strong, also prone to noise and fading. Both 160 and 80 really come alive in the winter nights when static is lower.
What about 40 meters? That always seems busy.
40 is really versatile, usable day and night. During the day, you get shorter paths, maybe regional contacts via the E layer, often needing higher angle antennas. At night, the F layer takes over, distances stretch out, often globally. Noise drops compared to 80 meters. Great all-around band.
Okay, moving up. 30 meters.
Now we're getting into territory often better for DX long distance. 30 meters can work day and night via the F2 layer. It has less D-layer absorption than 40. It's a narrow band, mostly used for CW, Morse code, and digital modes. A real favorite for DXers, especially when solar activity is lower.
And the king of DX bands, 20 meters.
Arguably, yes. 14 megahertz. It's the workhorse. Reliable daytime communication over thousands of kilometers is common. Often stays open well into the evening for global contacts, primarily F-layer propagation. Works well even during moderate solar activity and shines during high activity. Sometimes has that skip zone where nearby stations can't hear you, but distant ones can.
What about 17 meters?
Similar to 20, but more dependent on the solar cycle. During solar minimum, it might only open for a few hours midday. During solar maximum, it can be a fantastic DX band.
15 meters.
Even more solar cycle dependent. Excellent for DX when the sun is active, often worldwide openings. During solar minimum, it's mostly a daytime band, if open at all for long distance.
12 meters.
Similar story to 15, but amplified. Really needs good solar conditions. Can seem totally dead during solar minimum periods. Primarily a daytime DX band when it's open.
And finally, 10 meters, the highest HF band.
Right at the top edge, 28 megahertz. It behaves almost like VHF sometimes. Very, very dependent on high solar activity and high ionization. Can be spectacular for global DX during solar maximum, very strong signals. But during solar minimum, long-distance F-layer propagation is rare.
But it can have other openings.
Yes. It's known for sporadic E-propagation, especially in late spring and summer, unpredictable openings via patches of ionization in the E-layer, usually shorter distances than F-layer. It can also open via aurora, sometimes stays open after sunset briefly. It's an exciting but often frustrating band.
It really sounds like each band has its own quirks and responds differently to space weather. It's definitely not just one big shortwave experience.
Not at all. Knowing the typical behavior of each band and then watching those solar indices we talked about, that's how you learn to predict or at least make educated guesses about what you might hear and where you might be able to communicate.
So wrapping this up, that magic of shortwave signals hopping continents, it's really this incredible interplay, isn't it? Between the ionosphere high above acting like this ever-changing mirror,
That dynamic mirror.
and the sun constantly sending out energy and particles that shape and reshape that mirror minute by minute, day by day, year by year.
That sums it up perfectly. The ionosphere, powered by the sun, is the whole game. And if you understand, or at least track, those solar numbers, those indices, you get clues about how that mirror is behaving, which bands might work and when.
It's still amazing, though. Such a complex dance, but it boils down to the sun's energy, letting us talk across the planet with just radio waves.
Yeah,
It really makes you appreciate the sun's power in a different way.
it absolutely does. And, thinking about that constant change, the sun's cycles, it makes you wonder, doesn't it?
How so?
Well, for you, our listener, here's something to think about. Given that the sun is always changing, going through these cycles of high and low activity, how might future solar cycles, the ups and downs yet to come, influence this fascinating world of shortwave? Will the bands behave differently? Will technology adapt?
That's a great question, something to ponder. And if you want to keep track in real time, definitely check out resources like spaceweather.com or any number of amateur radio propagation sites. They're full of current data.
Absolutely. Keep exploring.